Hello and welcome to RF Design Tutorials. In this tutorial, we will talk about PIN Diode based RF switch design using Keysight ADS. The session objective is to walk through a design process which takes your ideal design and convert it to more of a practical design where your simulation result can be as close to measurement results as possible. Now, keeping time consideration in mind, I have decided to split this video into two-part tutorial. In the first part, which is this video, we will start with RF switch basics and then walk through a complete step-by-step design process of doing an SPDT switch design, ending with EM circuit, co-simulation and co-optimization. In the next video, which will be part 2, we will talk about measured result and comparison, and I will go through various best practices, troubleshooting, and offer practical design tips so that you can apply that in your own design work. To start with, let's understand the requirement of a switch, especially in today's communication system where you have multiple bands and you often need to switch between different signal paths or bands. So for this purpose, we need an RF switch. Now that can be constructed either by a PIN diode, which is one of the popular devices switch, especially if you are doing your design on RF PCB or RF board. Similarly, in IC technologies, you can use gallium arsenide or SOI kind of processes to design your own switch, depending on the form factor you need. Now, when it comes to PIN diode, the wide intrinsic region in the PIN diode makes it suitable for applications such as RF switch design, and that's what we are going to explore in this tutorial. Now, before we begin, I would like to extend my heartfelt appreciation to Professor Dennis Derrickson of California Polytechnic, San Luis Obispo, and his students for their collaboration in this case study. Now, let's start with understanding SPST switch, which is one of the simplest switch to understand. Simply means single pole, single throw. It has one input port, one output port as shown in this snapshot, and it's a basic switch which is basically used to either connect or break the connection in the signal path. From the circuit perspective, you can think of a series diode in the RF path, and by controlling the bias supply or DC voltage to that diode, it can be either put into forward bias or reverse bias condition, thus giving you the switching action we are looking for. Going forward, SPDT, which is more of a practical RF switch, it has one common terminal and two output terminals. By selecting the proper bias supply to each of the diodes in respective path, we can make one diode to be forward bias and keep another diode in reverse bias condition, thus signaling or paving the path of RF signal to flow from one branch to another. It's pretty simple again. Now, when we talk about SPDT switch, there can be two typical configurations, series and series shunt. What is shown to you in the left is pretty simple series topology, whereby switching one of the diode into reverse bias, we can create an open circuit. However, every diode, when it put into reverse bias, can only offer certain amount of attenuation or isolation. What if you need to increase the isolation? Well, in that case, you can also employ a diode in shunt configuration to the path, and then by controlling the bias supply, you can make it reverse bias or forward bias depending on the mode of operation. Like in this picture, assuming we want to connect the antenna to the transmitter path, in that case the V bias 1 will be set to positive. That means this series diode will be in the forward bias condition. Now the shunt diode is connected to V bias 2, which is basically the bias supply on the other branch, which obviously will be negative. Now in that condition, this diode will be reverse bias. That means it will be an open circuit to RF, so the entire RF energy will flow through the transmitter. But let's look at what happens in the receiver. So first, V bias is negative, so this diode is in reverse bias, and offer a certain level of attenuation. So you will have a leakage energy at the output of this diode. Now the shunt diode in that branch is connected to V bias 1, which is positive. That means this diode will be forward biased. So whatever is the leakage energy will go to ground as much as possible, thus increasing the isolation between RX and TX as well as RX and antenna terminals. Hopefully this explanation was simple enough for you to understand how the switch is working. Now if you need even more isolation compared to what can be offered by one shunt diode, you can think of putting in another shunt diode by keeping the return loss and impedance matching requirement in the mind. However, you are free to play with the topology depending on your isolation requirements. Now, when you think about PIN diode, is this diode with a wide undoped intrinsic semiconductor in between, and typically it is similar characteristics like a normal PN diode. So having this intrinsic region in between make it inferior rectifier, so that's why you will not see PIN diodes being used for rectifier application, but this intrinsic region is very handy when you think about building attenuators or switches, etc. Now in terms of characteristics, it follows standard diode equation for low frequency signal. At high frequency, this diode looks like almost perfect resistor. Now one of the key things to note, the high frequency resistance of a PIN diode is inversely proportional to the DC bias current. It is a very important property which I will go through as we go along in this presentation. This simply means by controlling the DC bias of your diode, you can change the resistance of the diode, thus playing a little bit with the attenuation or isolation offered by the switch. Also, the wide intrinsic region means diode will have low capacitance when reversed bias. So again, a couple of these properties will come in very handy when we go ahead with our switch design work. Now in a term of simple calculation, here is an example. So let's assume the capacitance in off state of a PIN diode could be, let's say, 1 picofarad at a certain frequency. Now for that frequency you can compute the reactance or capacitive reaction offered by diode, and let's say in this example is 497 ohm. So as a series element in a 50 ohm system, you can compute the off state attenuation or isolation offered by a single diode, and by using the simple formula we can calculate it to be around 15.5 dB. So similar logic you can apply in your own switch calculation. Once you know the off state capacitance, you can pretty much compute what kind of attenuation or isolation which can be provided by the diode. Now adding shunt elements, as we talked about previous slide, effectively reduces the source and load impedance, and hence it will reduce the impedance ratio and increase the off state attenuation. But then you need to also be concerned about the impedance matching because you are reducing the impedance ratio. And all these things you can try out in your design tool like ADS and come up with the right topology, which is the best compromise between the impedance matching, isolation which you can achieve, and so on. Now for our present case study, here is the switch design specification which we will design for, and during circuit design or optimization we will have little extra delta, whether when we are looking to optimize the switch performance in a particular frequency band. So we will add little bit of cushion on the lower side and upper side so that we have certain margin after fabrication. When we test the circuit, we are guaranteed to meet the specification which we are looking for. So here is the specification for you to reach. The important part is the overall PCB should be within 2 square inch, because as a part of PCB fabrication process, it directly affects the cost of the final product you are going to make. Now in terms of fabrication, we have selected Oshpark for this particular case study. They have many processes and we have selected 4-layer process. You can visit the website and look at a little more detail. Now with 4-layer process, we have access to the stack up requirement, We also have access to the material, and in this process they use Isola FR408HR, which is one of the popular PCB material if you are dealing with a medium frequency range kind of circuit design. So that's what we are going to use. Now in terms of the schematic configuration, here is a snapshot of the SPDT switch topology which we will implement. Now I have marked some important components in your switch design, which is here for you to see. Now one important thing, if you draw a vertical line around antenna input, you can see this is almost a mirror image on left and right side. And when we are dealing with switch design, it is preferable to keep the value of these components to be symmetrical so that you can have similar performance in both paths of the switch. But again, designers are free to choose the values and optimize them differently. But I would recommend keeping them exactly same and make use of variables in ADS when you are optimizing or changing the component values to get the right response from your circuit. Now in terms of device, again, depending on your design requirement like frequency, isolation, etc., you can go and do search of various vendors who can provide you with the PIN diode. For this case study, I'm going to use Infineon BAR50 device, and I have provided the link of this component in the description box of this video. One of the good things about this component is that we can download the SPICE model so that we can perform our simulation with high degree of accuracy in a software like ADS. Also, when you look at datasheet, I have highlighted some of the key specification which you can look for, and that can give you initial idea about the suitability of using this product in your design. In our case, if you think about insertion loss, which directly means the loss through the diode for your RF signal, you can see as you increase the bias current or DC current through the diode, your loss kind of reduces. Remember the previous slide where high frequency resistance is inversely proportional to the DC current. So by increasing DC current, we are reducing the resistance of the diode, hence reducing the insertion loss. So some of these things you could utilize when you do circuit design. Also in terms of isolation, you get a ballpark figure at a 0 volt reverse bias voltage, and you can see around our frequency we can opt to in something like 20 dB. So our overall requirement of isolation from our switch is around 30 dB. So that gives us good indication with series shunt we would be able to achieve the desired isolation. So some of these things for you to consider. Now when you download the zip file from the previously mentioned web link, you basically will get 3 files. D83, when you open it in Notepad or any text editor, you can see it is a diode SPICE model, and this is what we will import in ADS to create a nonlinear model. And also you have a package file which is denoted by SC79, and this gives you idea about package parasitics which you need to add on top of your intrinsic diode model, because package parasitics cannot be ignored over 100 MHz as noted in the README file. So as we walk through the design process, you will understand how to use these files in ADS for your own circuit design. Now I have provided all these links in the description box, and some of these references could be very useful to enhance your knowledge for RF switch design when you start working in certain design aspects as you go along. Alright, so that's enough for the introduction and basics of PIN diode and RF switch. The next sections will walk you through a complete step-by-step design process of doing RF switch design using ADS. This video is assuming that you already have a basic know-how of ADS, circuit design, optimization, electromagnetic simulation in ADS. If you haven't got the required expertise, I would say pause the video here, look at my YouTube channel, refer to Learn ADS in 5 minutes, RF Pro 5 minutes tutorials, etc. to gain the basic knowledge which is required to follow the remaining section of this video. But if you already have that knowledge, enjoy the rest of the session and wish you all the best in your design work. Stay tuned till the end of the video and don't forget to put in your comment, like the video and share the video with your friends and colleagues whom you think might be benefited from this tutorial. Thanks a lot and keep watching. As a step 1, let's start by creating an ADS workspace. Give it a name, like in this case we will give it a name pin_switch_example_demo. Now during workspace creation we can click on show advanced option and select to set up a layout technology. Now once we create a workspace, we can create a new PCB technology as per our need and as per our selected process. Here I will use a 4-layer process. Click on next, and here we can choose the default material, and after which we can of course modify whatever parameters necessary. Now in this case I'm using OshPark 4-layer process for our design. So by opening the 4-layer process specification, we can see the stack of parameters and the physical dimension. And also one thing to note here, along with this physical dimension, we also get access to material specification, like in this case Isola FR408 datasheet. By clicking on the datasheet, we can take a look at dielectric constant at our desired frequency and also the loss tangent, which we will use later in our stack up definition process. So noting these parameters will be helpful. So let's go ahead, click next and finish. Now workspace with the desired technology substrate is created, and here we can modify and cross-check whether all the physical parameters came up properly. First thing, we are going to define the through via to be a copper material. We will delete the blind via as the OshPark technology doesn't support blind or buried via. Now once we have the physical dimension correct, we can open material definitions and start modifying the property as per Isola FR408 substrate. So dielectric constant of 3.69 and loss tangent of 0.0091 at 1 GHz frequency as mentioned in the datasheet. So now we have our stack up ready and we can begin our next step. In this video, we will talk about steps to import diode spice model. As we already created the ADS workspace, let's go ahead and create a new schematic. Go to File, Import, and we will go ahead and select Netlist file and browse to the folder which we downloaded and unarchived from the vendor website containing the spice model. Here we will select D383, which is actually containing the spice model. Under options, we can choose to create a ADS schematic so that we can see the nonlinear model that we are importing. And we will go ahead and create a new library containing that model. Now here, if there is no error, you will see a successful message. Click OK. And now under library view, we can see the imported diode model. If you open a schematic, you can see a nonlinear diode model being placed, and all the spice parameters are read into this nonlinear model. Now in order to use this model for our simulation, we will need a diode symbol and associate this model with that symbol. Now here, by looking at various libraries, you will find a library called Devices Diodes, which contains different type of diode models and symbols. Here we will pick a diode symbol, place it on a schematic, and modify the model name to reflect the same name as our imported model, like in this case D383. We will connect input and output pins so that it is easy for placing this schematic as a sub-circuit. Let's go ahead and restart our workspace. Go to folder view, and here under folder view we can rename that imported cell to reflect the right part number. In our case it's bar 5002B. Now here, when you open a schematic symbol, you can see there is no symbol properly associated, and we will need a proper symbol to place this design as a sub-circuit. So let's go ahead and delete the symbol, right click and go to new symbol. So let's create a new symbol view, and here we can either create our own or simply copy the existing symbol. Like in my case, I will go and pick a diode symbol from our existing library palette. So now we have everything to use this device. In this video, we will talk about diode package modeling, which is very important for anything above 100 MHz. Looking at the folder which we downloaded from vendor website, you can notice a file which gives you detail about the diode package and its parameter, which is going to affect your high frequency performance. So the structure and the component values are provided, and the placeholder where the diode model has to be inserted. So let's open the schematic where we imported the diode spice model, and we can build around the package model around this diode symbol. So let's keep it side by side, and we can use the components available in the lumped component library, and we can simply start placing them into our schematic in the desired orientation as outlined in the document. After placement, let's go ahead and wire all these components up in a proper configuration with input and output pins, and orienting the diode in the right orientation. Now let's go ahead and modify the component values as provided to us in the documentation, and while doing so, make sure you don't mess up the syntax of the value and the units. So if you are new to ADS, you can always double click on the component and then modify the value. Here I'm doing on-screen editing, and now we are ready. In this section, we will talk about performing diode IV characteristic simulation. Now since we already have a diode along with package parasitics, we can go ahead and open a new schematic, and there we can drag and drop the diode symbol or the cell to place it on our schematic. Now we can also push inside the hierarchy and check the sub-circuit which we just created to make sure everything is good. Now we can go to library palette of sources, frequency domain. Let's go ahead and bring a DC power supply, and then to measure current across diode, we will go to probe components library and place a current probe. And also to control the current going into diode, we will place a series resistor. And now we will place a couple of ground terminals and make the wiring between the components as we need. It's a very simple series diode bias circuit. Let's go ahead and define 3.3 volts to the bias supply and keep the control resistor to be 50 ohm. From the simulation DC palette, let's place DC controller and rename the I probe as I_diode, which we will then plot in data display. Now we are ready. Let's go ahead and simulate our circuit and insert a table to plot I diode. And you can notice we have around 47 milliampere of current going through the diode at 3.3 volt and resistor of 50 ohm. Let's go ahead and place a new variable block, create a new variable called Vin, initialize it with 3.3 volts and assign the variable name in the DC supply. In the DC controller, we can sweep Vin variable from 0 to 5 volt in a step size of 0.1. So this will give us diode IV characteristics. Now you can see we have a small table, although it's truncated right now because of small size. We can insert a rectangular graph and plot I diode, which will have x-axis as swept Vin value. You can place a marker, and now we can read out the marker and notice the diode turn on characteristics and the IV characteristics. Here you can see at 3.3 volt we have 47 milliampere. Now to further control the current, we can go ahead and modify the resistor, and now you can see at the same voltage we have 4 milliampere across the diode. So this is how diode IV is verified. In this section, we will talk about a schematic design for our SPDT switch. Let's start with creating a new schematic cell, giving the name that you want. In my case, I will provide the name as SPDT switch design. Now once you have the new schematic, first thing we can do is to look at topology that we would like to create for our switch. Now to start with, we can drag and drop the diode subcircuits which we created earlier and place them in the desired orientation. You can use the rotate icon to rotate the components in the desired angle, or you simply use Ctrl R. For rest of the components, we will use components available in lumped component library, And I'm going to prepare only the left side of our switch design and then assign the variable values to all of these components so that we can keep our switch design to be symmetric in nature by assigning the same variables in both sides. Now we can go ahead and simply select the entire left hand side section, Ctrl C, Ctrl V to copy and paste, and use Shift Y and click at the reference location to mirror the circuit. Now once this is done, we have our switch topology in place. We will go ahead and attach a couple of power supplies for each of these sections, and because they have to be controlled in one path or the another, the values for voltage will be 3.3 and minus 3.3 so that one of the channel is on. We can right click on the wire labels and give the proper wire labels, and also the same thing on the shunt sides. Remember, it is going to be mentioned in a cross manner so that when series diode is on, the shunt is switched off. Now we can place 3 terminations for antenna, TX and RX terminals. Now next job remaining is to place a variable block and define the variables that we have used in our design. By changing the name equal to value method, we can directly type multiple values at the same time. And here, as you can see, we will use 5 capacitors, 3 inductors and couple of resistors for our design. In the values shown here, we will simply add those variables, and now we are all set to perform simulation on this switch design. In this section, let's talk about SPDT switch simulation and optimization. As we already have the basic switch done, let's go to simulation S parameter palette. Set up our frequency sweep range, which in this case is 1 to 4 GHz. Perform simulation and plot the relevant S parameter in terms of return loss, transmission and isolation. Now after plotting the graphs, we can place marker at the desired location, and as you can see at the current setup, port 2 is our output port, and the return loss is not really meeting the specification, whereas transmission seems to be okay. So we can go to Optim-Stat-DOE library palette, place view optimization goal and define our optimization criteria. In this case, I will keep my S11 to be better than minus 20 dB to be achieved from 1.5 to 2.5 GHz, and same thing, I will go ahead and define the transmission to be better than minus 1 dB in 1.5 to 2.5 GHz, which is slightly more than what we designing the switch for. Similarly, we can define goal for S22 and define the proper optimizer number of iterations. And now our next job is to define the variables to be exposed for optimization. So in this case, let's go ahead and switch on few of the capacitors and inductor models for optimization, leaving out the DC bypass capacitor. By switching to optimization engine, you can see very quickly we achieved the goal. So let's update the schematic and run the simulation with optimized value. Here we can see we have a good transmission and return loss, but the isolation is not what we expect. So let's go ahead and add another goal for isolation, and in this case it will be dBs31, and then the same frequency range for 1.5 to 2.5, and the isolation we expect should be better than 25 dB. So let's go ahead and run optimization again, and here we can notice few of the values touching their maximum. So we can go to edit variable and change the min-max range to let optimizer achieve the goal. And here error is 0. Let's update the schematic and rerun the simulation with updated value. And here we have the fully optimized switch circuit design, and we can move on to our next step. In this section, we will talk about prepping a schematic for layout generation. So far, whatever we have done is only keeping schematic view in mind, and none of these components really have a PCB footprint, so we can't generate the PCB layout from this schematic. Now, there is a library in ADS called lumped with artwork, which contains the component which have the footprint information. One of the components that I like to use is suffixed with pat. It is C pad, L pad, depending upon what component you are using. It has an electrical parameter as well as physical footprint parameter, and that we can use. But in order to replace all of these components one by one could be difficult. So we will use search, select by name, select all the capacitors so that all of them are selected in our design. Next we can go to edit, component, swap components. So here we will simply swap the current capacitor selected with CPAD model as shown here. By selecting that model and clicking on swap, you can see all those components have been swapped while still retaining their electrical parameter value, which right now is the variable name in the capacitor. Similarly, we can go ahead and select L, which is inductor, all the inductor components, go back to edit, components, swap components, and this time select L_pad1 and simply click on swap icon, and again inductors are swapped. Next, let's go ahead and do the same thing with our resistor component, which is again you have an equivalent component called R_pad1, and that is what we are going to use from the list. So with this simple operation, in no time we have transformed our electrical components to contain the pad information. Now we can refer to the size sheet, and in this case I'm going to use 0805 size component. We can read the dimension and we can update our W, S and L in each of these components. Now how we are going to do it? Again, we will select capacitor, inductor, resistor all together because all of these pad parameters have the same variable name. Then go to edit, component, group edit parameter value, and here we need to simply enter W, which is width, and enter the required width of that component. In this case is 1.5 mm. With one operation you can see all W parameters in all components are updated. Similarly, we will go ahead and update the variable S, which is basically the pad spacing and then the length of the component to be 3 mm. Now here with these three simple steps, we have transformed each of our components having the proper footprint size parameters. If you deal with mixed sizes, that's also okay. You can selectively pick and choose and update these parameters, for example like 04, 02 size and so on. Our remaining job is to create a layout for the diode component, and first thing we need to do is go to options, technology setup, and for the diode library we will add a reference library which has a PCB definition. Remember, we created pin switch example demo library to be 4-layer PCB technology. That's what we will refer here. So now we can go ahead and create a new layout for the diode cell, and here in the layout window we can create the required footprint. Now where do we get footprint information? If you go to the same Infinium datasheet, the part which we are using, which mentions the footprint information, and it's a very simple SMT footprint with two rectangles. And now in ADS layout we can create rectangle either exactly what mentioned in the datasheet or slightly bigger. In my case, instead of 0.35 by 0.35, I'm going to create rectangles with 0.4 mm parameters. Now here it is as simple as that. We will connect two pins which represents anode and cathode terminal, and it's exactly aligned to the schematic symbol we have. Now we can select one of the rectangles and go to edit, edge area pin, and mark that rectangle as the area pin, which will help us during layout routing. And same thing we will do for the other side. So now this footprint is ready with both of the pins available for layout purpose, and we can proceed for our layout generation. In this section we will talk about initial layout placement for our switch design. As we already have configured our schematic for all the components to be having the PCB footprint, we can start placing the components into layout. And here we will use the option of layout, place components from schematic to layout. We'll put the windows side by side so that we can see. Now here you can see all components are highlighted, whichever is not placed. we can simply click on one component, go over to layout window and click there to place. Once you're placing the component, the rubber band will show the connection in between those components, making it easy for designers to look at the right location where the component has been placed. So we can repeat this activity one by one and start placing all the desired component at tentative locations. Later we will fine-tune and rearrange these components into the suitable configuration to achieve best possible PCB size. So this step doesn't take too much of time and can be easily done within a minute or so to achieve initially placed layout, as you can see. Now we are ready to take the next step. In this section, we will talk about layout routing from our initial placement of the components in layout. Now since we have the components placed, we can go ahead and save our design with a new name, just to ensure we have a way to go back in case something goes wrong. So we'll go ahead and suffix the design with underscore layout name and save it in a new name. So now the entire cell has been saved in a new file, and we can start thinking about how can we place or rearrange these components to achieve best possible PCB size. So here, based on the rubber band information, I'm going to mirror certain components, rotate certain components. Some of the quick keywords which will be helpful is shown to you on your screen right now. Shift X, Shift Y, Control R and M. These are very useful commands to remember when you are working with layout in ADS. So here I'm just doing some initial manipulation of the component placement and trying to rearrange in a fashion where it is easier to route or interconnect the components. So now once it is done, we will go ahead and create an outline of our PCB in desired size. We can pick any layer from the list. In this case, I have picked up a bounding layer. And here I'm going to insert a coordinate of 0, 0 and then 50, 25, essentially to create 2-inch by 1-inch kind of overall PCB size. Now once we have it, let me push some of these components at the bottom. And now since we have to use SMA connector for our final PCB, I'm going to create a line of width 0.8 mm and a length of 5 mm to allow for center pin of the SMA connector to be soldered. Here I'm going to simply draw the trace in the desired layer which I want, and you can use the snapping options like midpoint, etc. to be more precise. So once we have the line of around 5 mm length, which will be sufficient for SMA lead soldering, we can end the trace. And now I'm going to copy with Ctrl C and Ctrl V at two other locations, which is basically going to map it to antenna, TX and RX port, because this is the SPDT switch. And I'm going to place antenna terminal on the bottom edge, and left and right will denote basically the TX and RX. Once this is done, we will make the layer to be unselectable from the panel so that we do not disturb this. Now we can move over all of our initially placed components, and again we can simply select all of them, press M to move, pick one of the components which is going to be aligned with input line, and we can go ahead and place it. Now since we have a pretty good idea of the target PCB size, we can start rearranging the components to fit within the given amount of PCB size, and also keeping in mind the separation which you need to maintain between two components for easy soldering later. And again, different people might arrange the PCB differently. Now let's calculate 50 ohm line impedance using CILD. I'm going to optimize the width of the line to achieve 50 ohm target impedance, and in this case it's 0.4 mm. So now we know the trace width which I need to use. So I will go ahead, set up my trace to use truncate end style, corner type as mitred with 50% of cutoff ratio about metering to ensure smooth transition whenever we have to bend the trace as and when required. And again, this is a fun job to do in ADS using trace command to route. And again, if you feel the trace is going slightly oblong, not perfectly perpendicular, you can stop just before the trace and then use the corner point to stretch it in the desired direction. like I'm showing you here. Again, it takes a little bit of practice, but not a whole lot of time, and you would be up and running with the config. Now I need to connect the input to the point, and I need to cross over the supply voltage. So here I'm going to draw a trace, click on the screen and press period key to move to next layer, and then press the comma key to come back to the layer. These are very useful shortcuts, and the via will be automatically inserted from the PCB technology. And again, we can select the trace, press M to move at the desired location, then pick one of the vertex points to make connection to the desired point, which is basically in this case the antenna input getting divided in two sections. And again, by selecting the trace and the vertex points, you should be able to manipulate how much separation you need in layer number 2 so that you don't end up shorting your trace with the top layer. Alright, so now only thing we need remaining is to have two pads where we will solder the bias supply wires. And in this case, I'm going to create 2 mm by 2 mm rectangular pad and place it at appropriate place for VS1 and VS2, which is basically a positive and negative supply. Now once that is done, I will make the initial layer to be selectable, select 3 end lines which we placed originally, and from properties window in the layer, we will go ahead and change the layer to be cont, which is the top layer in our stack up, and suddenly you will see everything lights up. Now only thing remaining now is to make this incomplete connection to be complete. And then as soon as we are done, our layout is ready with everything routed properly. Now let's talk about finalizing our layout, which is ready for EM analysis as well as fabrication. So we will start by insert plane, enter the clearance to be 0.6 mm in this case on the con layer. Use the bounding box as a guiding light to pour the copper. Similarly, on M2 layer, we will use clearance of 0.2 and pour the ground to create clearance and have the ground plane. Now remaining job is to stitch the ground plane and also clean up a little bit. We can double click on the ground plane, remove the island, and enter the area below which anything has to be removed. As you can see, I just removed few things. Also, we can apply certain smoothing to create a proper looking ground plane instead of ugly looking ground plane in our structures. Alright, so now we have con2, which is a through via layer. So we will go ahead and create a circle, provide the desired radius of our via hole, and one circle is created. We can go to edit, copy, paste, and then step and repeat. Enter the X spacing, Y spacing, and create a kind of array for the desired number rows and columns. And we can go ahead and start placing these via arrays to make sure we have a proper ground stitching between the top layer and the bottom layer. By doing this process, once you place the layers, you can notice there is a minor blue cross in each of these circles, and that's happening due to the net mismatch, because the vias which we are placing doesn't have any net name, and the ground which we poured has a net name called GND exclamation. So we will resolve this as we go along, but let's go ahead and place as many via as we want across the ground plane to make sure we have no parasitic capacitance kind of getting formed as a parallel plate between two layers. Now to merge the ground plane, simply click on one of the objects, click on the blue dot, resolve the net conflict, and you can merge. So now you can see all the via circles become normal color. And again, we can use the single via to place, put a spatial emphasis where your components are getting grounded, and again resolve and merge the nets as and when required. So this operation doesn't take too much of time, and as you can see, we have a nice copper pouring along with via planes, and now our layout is ready for electromagnetic analysis. In this section, we will talk about EM simulation setup and the steps needed to run EM analysis. We will start from finalized layout and start placing a pin by giving a proper identification name so that we can recognize it in our EM setup. So here we will need 5 pins, namely antenna, TX, RX, VS1 and BS2. So we can either provide name while placing the pin or after all the pins are placed by double clicking. Now once all the pins are placed, we go to Tools, RF Pro, create a new setup. Now RF Pro is the new EM simulator in ADS, which has a brand new interface with a lot of capability. We will give the view name RF Pro _ FEM, select the right stack up and click OK. Now the RF Pro window will read the entire layout database, and we can even see the geometry in 3D manner. Here you can get all the nets, all the components. So first of all, we will select all the components, right click and switch them to circuit role, because these are discrete SMT components which have no role in EM analysis. Also, to take care of pad parasitics, we can right click on components and include area pins. Now the pads of these components will be included in simulation. But if your SMT model already has these pads, don't use this feature. Here let's go ahead and right click to delete the user defined EM, because we want to run a full EM of this entire board. We can select all the pins to create board, but we need a ground pin. So we right click on reference pin layer and define M2, which is our ground layer. Now we can drag and drop pins over to ports, and once we click on port, we can render the geometry in 3D and look at plus and minus terminal for each of those ports. So the port creation is done. Now we need to add components into our analysis. So we select all the circuit role component, drag and drop. This way RF Pro does partitioning of what is needed to be EM simulated and what is not. Anything added in component model will not be EM simulated. Now we double click on option, set our frequency sweep range, in this case is DC to 4 GHz, and from simulator we will select FEM, which is a full 3D FEM simulator, but you also have choice of selecting momentum, which is 2.5T. Now we are all set. Double click on run to run the analysis. Now since this is a little complex board, it will take some time, so I will pause the video. Now the simulation is finished. Now we have all the results, and it took around 18 minutes on my laptop to perform full 3D analysis. Just to do sanity check, we can expand results, open the S parameter to plot certain S parameter results, but these are not complete since the SMT components have not yet been integrated. Now we can generate the test bench or a sub-circuit so that we can perform circuit simulation with a combination of EM data and circuit component. Here you can see the resulting schematic design. Now let's talk about EM circuit co-simulation and co-optimization. As we already have the EM circuit co-simulation schematic created by RF Pro simulation, where you can see 53 port S parameter file, which is duly connected with all the components which we marked as circuit role, and also 5 terminations. So first thing we will do is change the termination to have a DC source, because at that point it's the switch drive voltage which we need to feed. So essentially we will have 3 terminations. We will delete the S parameter controller which appears by default, and we will copy our optimization goal and the simulation setup from our original schematic design. Here you can see all the circuit component values which we achieved during our circuit simulation, but that didn't had layout parasitics. Now let's go ahead and plot this parameter response for our co-simulation. Here you can see due to the PCB parasitics, the response is not correct, and also we will need to change the bias supply voltage so that we have the second port as the output port, since our all optimization goal was set as per S21. So it's not a big deal. Now we need to optimize these circuit components to take care of PCB parasitics. So let's start optimizing and retune the lumped component values to try to take care of the PCB parasitics. As you can see, few components are touching their max limit, so we can open the edit variable plot and we can start changing min and max of these components as may be required in order to achieve the best possible optimization result. Now a lot of this depends on how good PCB design you have done. because if you end up introducing a lot of PCB parasitics, it may not be possible to fully compensate for it by simply changing the discrete value. Here you can see the error function, the contribution of each of those goals, what they are having in overall error function. And again, when you see how optimization is progressing, which goal is contributing, where it is missing, we can start balancing out some goals if required. We can save the goal. We can go ahead and change certain optimization goal on the fly, while also storing some intermediate result in case you have to go to that point. Here we can trade off a little bit of return loss to achieve better isolation. As we can see, the isolation was little struggle to achieve in the wide frequency range, and it's always counterproductive. That means to achieve better return loss, we have to sacrifice a little bit of return loss. But here, it's designer responsibility to trade off, what kind of goals are more realistic and how they can balance the performance. So here, in interest of time, I will stop the optimization, update the schematic, and now let's run the schematic with optimized values which we have achieved. And here you can see we are able to recover good amount of performance for our switch design. So this circuit is now fully optimized, including the layout parasitics. Now let's talk about achieving final circuit values and performing statistical analysis on our design. Now initially, when we started optimizing our circuit, we left it free flowing. That means we didn't put restrictions on any specific values or order on which these values have to be achieved. So we can now go ahead and find the nearest possible realistic values of these components and modify the values as per the available, either the inventory which you already have in stock or something which is available from the vendors. So here, as you can see, I have rounded it off to the nearest standard values. Now before we proceed, we already have an idealistic response. We will switch on the history so that these traces remain there, which will allow us to see the differences occur due to the value change. And here in the resulting graph, you can see there is not a whole lot of change in terms of circuit response based on our rounding off to achieve the final BOM, which we can buy and include in our PCB fabrication or assembly. So let's go ahead and switch off the history. So now in a way we have the final value of the circuit components that we will use. But before we fabricate the PCB, we can go to OptimStat DOE palette, where you have a lot of different type of statistical analysis. And here in this video, I'm only going to explain about Monte Carlo. So the setup is quite simple. We just need to put our simulator name in double quotes. In this case is SP1, which is name of our S parameter simulator. We can choose the number of iterations, and we will save all iterations so that we can see the overall spread. Now we go to simulate, simulation variable setup. Under statistics tab, we will enable statistical variation on all the components. Again, you can choose the distribution, the format, either plus minus absolute value or percentage. By default, ADS will have values as per plus minus 5% in terms of absolute number, but you can change it based on what components you are buying and going to use in your PCB. Let's go ahead and run simulation. And here now you can see various Monte Carlo iterations are being run, which is basically changing all those lumped element values in a statistical fashion, either using a uniform distribution or Gaussian distribution. Once all iterations are complete, we would be able to see the impact of those variations in our circuit performance. Here, let's try to zoom in near S11 and see the spread of S11 due to changing component values due to their tolerances. And here you can see largely in our band everything is better than minus 10 dB, which was one of our design goal. Similarly, by going close to S21 and zooming into the graph using the icon, here also you can see largely the insertion loss is better than 1 dB, except 1 or 2 outliers which are giving more insertion loss. But again, This is pretty decent, our isolation is good, everything is nice, so we can proceed for next step. Let's now talk about how to generate Gerber and drill files so that we can fabricate the PCB. In last section we talked about finalizing the BOM values, and also we saw this PCB layout is okay for our switch design and we can take care of all the parasitics. So by going to File Export, you can choose the file type. In this case is Gerber and drill. Going to more options, you can define the proper format as recommended by your fab house in terms of scale factor, output units, format, etc. In layers, you can select positive or negative based on your fab house recommendation. Here, as you saw, I left out the via layers because it's already included in the drill, and that's fine. We will switch on view file after export. Although it's a deprecated feature, but it will still show you the Gerber output. And here you can see all the layers which are involved. So let's go ahead and switch on one by one. So that's your top layer, which is con. Then we have M2, which is our second layer, third layer, and so on. And now you can also plot the drill file, which is, so that you can check the holes visually. And here you can see all the drill holes are included. Now, where does this file get generated? If you right click on the workspace name, go to Explore in File Explorer, under Manufacturing, you will find the Gerber and you can see all the layers with the default extension. Of course, you can change this extension as per your fab house. Let's open drill file and here you can see all the details about drill. So we are all done with our PCB. Thanks for staying so far. I hope the content presented in this video was helpful for your design application and you have taken time to pause the video and follow some of the steps shown in the tutorial. In part 2, the video which will come up very shortly, we will talk about measured result and comparison of simulation versus measured. We will also go through few best practices, troubleshooting skills, and practical design tips. So stay tuned and thanks for watching so far.